In this problem, we're given a sequence, and we are asked to find the equation for the sequence and then find the 10th term using that formula. So right away, you want to first identify the pattern on how we're getting to each term. Here we're multiplying by 2, multiplying by 2, multiplying by 22, or by 2 as well. So that tells me that we are looking at a geometric sequence. And so to write the equation for the geometric sequence, to find any term that we wanted, we're going to start with the 6, and we know we're going to multiply by 2. Well, the question is how many 2's would we need to multiply to get the term that we want? So to get the second term, I multiply by 1 2. To get the third term, I multiply by 2 2's. To get the fourth term, I multiply by 3 2's. So I'm always multiplying by 1 less 2 than the term that I'm searching for. You could check to make sure this is right. Plug in 4. 4 minus 1 is going to give us 3. 2 to the third is 8. Times 6 is 48. So we know that this equation works. All geometric sequences will have this same form where we take the first term times the common ratio to the n minus 1 power. From here, we can now use this equation to find the 10th term simply by plugging in 10 in for n. We need to subtract first, so this will be 6 times 2 to the 90, or to the 9th. From here, if we take 2 to the 9th power and multiply that by 6, we will end up getting our 10th term to be 3072. Now, in the next problem, we're going to see another geometric sequence, except our goal is going to be a little bit different. So here we have our first 3 terms, and it might not be very obvious what we're multiplying by to get the next one. But to make sure that it is geometric, we can take 48 divided by 36 to get that common ratio of 1.33. Verify that it's the same by taking 36 divided by 27. Again, I get 1.333. Now, I don't want you to write your common ratio as 1.33 because then you're chopping off a lot of that decimal. Instead, we could write that as 4/3. That way our common ratio is perfect. And so for our general formula for T sub n, we're starting with 27, multiplying by 4/3, and that would be to the power of n minus 1. So our question is asking us to find what number n would give us the number after the ellipsis. And so the ellipsis is the 3 set of dots. So if this is a term, we're looking for what term it is. We're looking for n. And so for this problem, we're going to set this number. Notice it's going to be an approximate answer since it looks like it was a decimal that was rounded. And we're going to set this equal to our function. The first step is to get rid of this 27 by dividing both sides by 27. So we can take this large number and divide that by 27. So even though my answer on here is going to be a rough estimate, I'm going to keep that entire number in my calculator just to make sure that we remained accurate. Oh, and our 27 is gone now. So we just have 4/3 to the n minus 1. So we're searching for n, it's stuck in the exponent, and so to undo this we are going to need to use a logarithm where we're going to take the log of both sides. So I have the log of 9,954.96 is equal to the log of 4/3 to the n minus 1. Now the reason why we did this is we can bring this n minus 1 out front times the logarithm. And so now to get n alone, I'm going to divide both sides by the log of 4/3. So I'm first going to take the log of this 9,000 number and divide that by the log of 4/3. And so we end up getting a perfect 32. Had I not been using these entire answers in my calculator, we probably wouldn't have got something that nice. And so we end up getting 32 is equal to n minus 1. So our last step is to add the 1 over. And so n is 33. So what that tells me is that the 33rd term was this guy right here, the 2,000 268,783.9523. So we found that we would have to find 33 terms before we would run into this number.